Hey guys, Mr. Backberg here. In this video, we're going to look at Newton's law of cooling. The rate of change at which an object's temperature is changing at any given time is roughly proportional to the difference between its temperature and the temperature of the surrounding medium. This observation is called Newton's law of cooling, although it does also apply to warming as well. So if you've got a cup of hot soup that's sitting out, it's going to gradually cool down to the surrounding air temperature of the room. Or if you've got a hot silver ingot that's been immersed in some cool water, it's going to drop down to the temperature of the surrounding water. So that's the kind of stuff we're talking about here. Now, because we have that sort of proportional relationship, then we can write out a differential equation to represent this situation. So if capital T is the temperature of the object at time lowercase t, and if we let capital T sub s be the surrounding temperature of the medium, whether that be air or water or whatever your object is in, then we can write out the differential equation d capital T d little t is equal to negative k times the difference of the object's temperature minus the surrounding temperature. And using that and what we've seen about the law of exponential change, we can then write out Newton's law of cooling. So Newton's law of cooling says capital T minus T sub s is equal to T sub 0 minus T sub s times e to the negative kt. Now that T sub 0 in there represents the temperature of our object at a time of 0. Now, a lot of times you'll see this equation rewritten to have this capital T on the left-hand side all by itself, so adding this T sub s over to the right-hand side, and that's actually the form that I prefer. So I'm going to say capital T is equal to T sub s, because we're adding that over to the other side, plus the difference in the initial temperature minus the surrounding temperature times that e to the negative kt. So in this example, we're going to look at using that Newton's law of cooling. So we've got a hard-boiled egg that is at 98 degrees Celsius, and it's put in a pan under running 18 degrees Celsius water to cool off. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. We want to figure out how much longer it's going to take the egg to reach 20 degrees Celsius. So we're going to use that Newton's law of cooling. So T equals T sub s plus T sub 0 minus T sub s e to the negative kt. Now, using the information that we know from the problem, the surrounding temperature is the temperature of the water that's running over the egg. So we're going to let T sub s be that 18 degrees Celsius. Our T sub 0 is the initial temperature. So we were told that our egg started at 98 degrees. So that's the first part, but then we also knew that the egg cooled to 38 degrees after 5 minutes. So we're going to let capital T be 38, and we're going to let little t be 5. So we can take those 4 pieces of information and plug those into this equation, and what that's going to help us do is solve to figure out this cooling factor K. Now, once we know what that cooling factor is, we'll be able to figure out how much longer it's going to take us to cool down to 20 degrees. So plugging all that stuff in, this says 38 is equal to 18 plus the difference in 98 minus 18, e to the negative k times 5. Now, there's some simplifying that needs to happen in here because we're trying to solve for k. The first thing that I'm going to do is subtract that 18 over to the left-hand side. So 38 minus 18 is 20 equals, now if we do this subtraction inside of our parentheses, 98 minus 18, that's going to be 80 e to the negative k times 5. I'm going to divide that 80 over to the left-hand side, and I'm going to leave it as a fraction. So 20 divided by 80 is going to be 1/4. And then this is equal to e to the negative k times 5. Now we've got a little bit of an issue because that k is up as a power on that e. So to get rid of the e, we're going to have to take the natural log of both sides. So those will cancel out. So we'll have the natural log of 1/4 is equal to negative k times 5. Now I'm going to change that natural log just a little bit, just because we don't like to have fractions in there. So remember, we can rewrite this as the natural log of 4, but we need to make it negative. And this is equal to negative k times 5. I want to get k all by itself, so I want to get rid of the times 5, but also get rid of the negative. So I'm going to divide both sides by -5. So on the left-hand side, when I do that, the double negative will turn positive. Now I'm going to rewrite the left-hand side as 1/5 times the natural log of 4, but then that 1/5 I'm going to turn into a decimal. So I'm going to call it 0.2 times the natural log of 4. That's going to be our cooling factor K. Now what I can do with that is I can take that and plug that into our Newton's law of cooling formula. So we've got T equals, now remember our T sub S value was 18, plus inside of our parentheses we had 98 minus 18 e to the negative k. Well, we know what k is now, so we can fill this in. 0.2 natural log of 4, and then all of that is being multiplied by our t value time. Now that we know what that cooling factor K is, we can use this equation to help us figure out when our temperature is going to reach 20 degrees. And I'm actually going to do that graphically on my calculator. So in my calculator in the y equals screen, I've got our Newton's law of cooling equation typed in. Now I went ahead and did the subtraction that was inside of those parentheses. The 98 minus 18 is where I'm getting the 80 from. And then we're trying to figure out when this reaches a temperature of 20 degrees. So in my y2, I typed in 20. Now I did adjust my window just a little bit. So my x's are going from 0 to 20 and my y's are going from 0 to 40. When I hit graph, we're going to get a picture that looks something like this. And what we're looking for is the intersection point between our two lines. So I'm going to do second calc, and I'm going to check where my lines intersect. I'm going to go close to the intersection and hit enter 1, 2, 3 times. And it tells me that this is happening at an x value of 13.3. So if we think about the context of our problem here, we just got an x value of 13.3, or we got a time of 13.3. So that's the total time that it took to cool from 98 degrees down to that 20 degrees. But we already did some measurements that told us that it took 5 minutes to cool down to 38 degrees. So using that, then it would take a little bit more than 8 more minutes to get down to 20 degrees from when we measured it at 38 degrees. That's going to be it for this video. Thanks for watching.